Why bigger wind farms are less effective. As climate change accelerates and energy demand continues to rise, countries are racing to replace fossil fuels with cleaner sources of power, such as offshore wind. In regions such as the North Sea, plans are underway for a dramatic expansion of offshore turbines, with the hope that wind could supply a large share of Europe's future power. But how much energy can we realistically extract from the air? A new study by Ole Anders Nust suggests that the answer is shaped not just by turbine technology or clever layout design, but by the physics of the atmosphere itself. When wind turbines generate electricity, they slow the wind down. Behind every wind farm is a wake, a stretch of calmer, slower moving air. As more turbines are added and wind farms become larger, these wakes overlap and reduce overall efficiency. This effect is well known. What Ole Anders Nust wanted to understand was whether there is a deeper physical limit at work. Instead of relying solely on detailed computer simulations, Nust examined the basic energy balance of the lowest layer of the atmosphere, known as the atmospheric boundary layer. This is the part of the atmosphere that directly interacts with Earth's surface and with wind turbines. The key idea is simple. Wind farms can only produce as much electricity as the atmosphere supplies in the form of kinetic energy. Three processes feed energy into a wind farm: winds blowing in from the sides, pressure forces acting across the whole site, and turbulence drawing energy down from faster moving air above. That last source is crucial, but it only works within the atmospheric boundary layer, where turbulence is strong. This means the energy available to a wind farm is spread across the full depth of that layer, not just the air immediately around the turbines. Turbulence makes the boundary layer energy accessible, but only incoming wind and pressure forces replenish it. Crucially, the sideways supply of wind energy scales with a farm's perimeter, while the farm's area grows much faster. So as wind farms expand, that edge-driven energy becomes less important per square meter, and farms must increasingly rely on large-scale atmospheric pressure processes to replenish their supply, a process that has limits. To test this theory, Nust analysed production data from 31 offshore wind farms in the North Sea, finding that the 23 largest followed the pattern predicted by atmospheric physics. The remaining 8 did not produce enough to reach the atmospheric limit, and therefore did not follow the predicted pattern. The results were striking. Small wind farms can generate over 6 watts per square meter, but as farms grow toward 1,000 square kilometers, output falls to around 1 watt, leveling off at roughly 0.8 watts for the largest sites. The implications are sobering. Europe consumes 15,000 to 20,000 terawatt-hours of energy each year. Even covering more than 500,000 square kilometers, essentially the entire North Sea, with turbines would meet less than a quarter of that demand. Offshore wind is a vital part of the clean energy toolkit, but the atmosphere itself places a ceiling on how much it can deliver. The search for fossil fuel alternatives must look further.